Look at the full trajectory of a piecewise affine Collatz-like map, and you are immediately confronted with a sprawling exponential mess, trillions of cascading pathways tangling into an infinite chaotic web. But trying to solve the entire system at once is a mathematical trap. To actually understand this structure, we have to cut away the noise and isolate just a single arbitrary path. We rigorously define this isolated branch using 3 parameters: its specific length, h, its binary itinerary of operations, epsilon, and its canonical carry word, n. These parameters lock in the local rules of our chosen sequence. That lets us ask a precise question: what is the complete realization space for this exact branch? In other words, out of all possible numbers, which starting values and moduli successfully navigate this sequence while satisfying both the strict closure requirements and the positivity constraints? This realization space is algorithmically decidable through a 3-stage mathematical funnel. By passing a branch through these filters, we can precisely classify its behavior. We have to map the rigid algebraic rules of these individual sequences first. Only then can we piece together the global, varying modulus dynamics of the entire system. Stage 1 is the algebraic gate. Any closed loop must satisfy the affine endpoint identity, Km minus Bx sub 0 equals sigma s. K and B are structural constraints, and S is the weight functional. X sub 0 and M must be whole numbers. That creates a strict bottleneck. For a closed integer endpoint solution to even exist, this continuous line cannot simply float in the plane. It must strike exact integer coordinates on the lattice. This brings us to Theorem 2.1, the linear Diophantine criterion. It acts as our absolute primary filter for all potential branches. An integer solution exists if and only if the greatest common divisor of k and b perfectly divides the functional s. If a branch fails this divisibility test, it yields an empty set and is discarded. But if it passes, the system locks onto those lattice points. We then extract the exact coordinates to compute the reduced baseline quantities, d, b0, and m0. Theorem 2.1 ensures we only process viable paths. It cleans the board before any continuous geometric analysis is even attempted. Once a branch survives the algebraic gate, its infinite potential solutions are parameterized along a continuous axis, tracking a new variable, t. But t cannot roam freely. It is bound by a discrete congruence class constraint. T is congruent to a specific residue modulo Q. The system's parity and integrality conditions aggressively restrict all valid mathematical solutions to exclusively sit on these evenly spaced discrete points. With the candidates isolated, we move to the next phase of the funnel. We process the remaining positivity, box, and floor quotient constraints as a series of affine inequalities. These mathematical affine inequalities will operate directly on our newly established parameter line. We apply those affine inequality constraints to the parameter line procedurally. Every inequality acts as a half-line boundary. It slices away one side, leaving only the dots satisfying its rule. Layering this finite list forces a mathematical intersection, carving out a bounded interval. This brings us to Theorem 2.2. The realization space is strictly forced into one of exactly 3 geometric outcomes. Outcome 1 is the empty set. If the half-line constraints overlap and contradict each other, every point is eliminated. Outcome 2 is a finite arithmetic segment. The boundaries form a closed box, trapping a discrete set of solutions between a lower and an upper limit. Outcome 3 is an eventual arithmetic progression. The surviving space is capped on the left, but extends indefinitely to the right toward positive infinity. The strict algorithmic rule for this is straightforward. An infinite progression occurs if and only if no surviving inequality possesses a negative slope. This geometric sieve constraint guarantees complete mathematical decidability. We can perfectly classify the exact size and shape of any branch's realization space simply by evaluating its affine bounds. We know how to solve a single branch, but doing this across the infinite tree requires us to neutralize the system's massive combinatorial redundancy. We do that with Theorem 2.3, rotation invariance. Take any completed symbolic cycle. If you cyclically reroute the starting point, the reduced ray quantities in the center, d, b0, and m0, remain perfectly static. Next, we analyze repeated block sequences using Theorem 2.4. The logic here depends on the map's scaling factor. Because the slope lambda is derived from powers of 3 and 2, it can never equal 1. Thus, the unique fixed point of a repeated sequence is mathematically forced to equal the fixed point of its base block. If the repeated string closes, the original block must have already closed. Any subsequent condition in that string is just an exact scaled copy. The realization space of the long chain collapses entirely into the realization space of the single base block. This means block repetition adds no dynamically novel constraints to the system, allowing us to focus exclusively on primitive, unrepeated base strings. Theorem 2.4 allows us to safely discard infinite strings of repetitions from our analysis. We actively filter out all of that infinite redundancy from the system, leaving behind only the true primitive periodic branches. To handle the surviving closed loops, we introduce Corollary 2.5, which applies classical Mobius inversion and necklace counting directly to the structure. This combinatorial formula executes the final bookkeeping, computing the exact number of primitive periodic branches that exist for any given length h. Fixed branch theory provides a systematic, sequential decision funnel for any arbitrary path. We verify integer existence via Diophantine algebra, bound the resulting set using 1D affine geometry, and collapse redundancies via strict combinatorics. With the local branch arithmetic completely closed and decidable, the theoretical groundwork is clear. We are now positioned to analyze the global winding cocycles of the broader Collatz structure.